All right, this is the section 1.4 Fractional Expressions pre-class notes. Our objectives in this section are to define a rational expression and to find the domain of it. Domain means the values that you're allowed to plug in because they give us a real number when we get the output. We're going to simplify rational expressions, and we're going to work with operations of rational expressions. So a fractional expression is a quotient of two algebraic expressions. And as a special case, what we consider our rational expressions that we work with are the ones where we are dealing with two polynomials. So a polynomial on top and a polynomial on bottom. So I consider both of these rational expressions. This could be considered fractional as kind of the generic name, because we might have a radical or something else in it, but what we're focusing on is two polynomials. So since division by zero is not allowed, the domain of P over Q consists of all the real numbers except those that make the denominator equal to zero. So we really don't want our denominator to equal zero because that is an undefined value. So for example, if this was our polynomial over polynomial, so this is a rational expression, to figure out what makes the denominator equal zero, we typically try to factor it if it's one variable, or sometimes even two, but especially if it's one variable, you can tell that -3 and +3 would make those two different factors equal zero, so that we have to say that it's all real numbers except plus or minus 3. Here, this is a little trickier because we just don't want the denominator to equal zero, but they're both variables. So if you think about isolating the y, we just don't want y to ever equal x to the third power. So again, we won't be dealing with any like that. Our domains are always going to be things that we can solve a number for. This is a property that we'll need to know, is that if you have something that is on top and something on bottom, and they have a common factor, so here the common factor is d, you can pull that out of each of those and then it reduces to 1 because anything over itself is 1. So this is really how we reduce fractions in our head anyways, but this is just showing it to you as a property. So we sometimes describe this simplification process by saying that a common non-zero factor in the numerator and denominator of a quotient may be canceled. A rational expression is considered to be simplified or reduced to lowest terms. That's really important. Reduced to lowest terms is the same thing as saying simplified. If the numerator and denominator have no common polynomial factors of positive degree and no common integral factors greater than 1. Okay, so we're ready to jump right into our examples. This first one is something that's not really based in this class, but I wanted us to make sure we understood how to add and subtract just general fractions together before we throw variables in. So when you're adding or subtracting two fractions together, you have to get a common denominator. So we need a common denominator to add or subtract fractions. So we have to think about what would be a common denominator for 54 and 72. Now, if you don't know off the top of your head, one way to find a common denominator is to list multiples of each number. What we mean by multiples is you say, what's 54 times 1? Well, that would be 54. 54 times 2 is 108. We might want our calculator beyond that point. 54 times 3 is 162. 54 times 4. Another way is just to add 54 each time. It's 216. So what I normally do is I list about 3 or 4 from one group, and then I go and do the other group, and then I just keep working back and forth until I find if they have a match. So 72 times 2 is 144. 72 times 3, I want to say, is 216. Let's see if I'm right. Yes, it is. So the least common denominator is 216. Now, the reason I like this method of finding your LCD for numbers is because now you know what to multiply by. So we need to create a 216 in the bottom of each of these fractions. So to do that, we have to multiply by 1, 2, 3, 4, because it was the fourth multiple on top and bottom. And for 72 to turn into 216, we need to multiply by 3. So this would be 44 over 216 minus 21 over 216. 44 minus 21 is going to be 23 over 216. I don't believe that reduces, but you would need to check all the factors of 23, which is 1 and 23, and make sure they don't divide evenly into 216. 1 goes in, but it's not going to reduce the fraction. Okay, so now we want to talk about rational expressions that have variables. So to simplify a rational expression, we factor both the numerator and the denominator into all of the prime factors. That means as far as we can go. And then assuming the factors in the denominator are not equal to 0, you can cancel any factors that are on top and bottom that are in common. Adding and subtracting with rational expressions. To add or subtract two rational expressions, you find a common denominator and you use the following properties. So once you have a common denominator, you add the numerator or subtract the numerator, and the denominator stays the common denominator. If the denominators of the expression are not the same, we need to obtain a common denominator by multiplying the numerator and denominators of each fraction by a suitable expression, just like we did in the last example. Typically, to figure out the suitable expression, we use the LCD, which stands for the least common denominator. Of the two quotients. To find the LCD, you usually factor all of the denominators completely into primes, which means as far as they can go, and then we form the product of the different prime factors using the largest exponent that appears with each prime factor. I'll show you what we mean by that on an example in class. I'm going to do pretty much just a basic example in a minute for the adding and subtracting, and then we're going to do a secondary one when we have our class session. So let's just look at this very first example. This is not multiplying, dividing, adding, or subtracting. It's just simplifying an expression. Typically, you want your polynomials to be in descending order when you try to do this. So that means highest power down. So we actually need to reverse this. This is negative r squared plus r plus 12. We're just putting it in the order of descending order. The bottom is already in descending order. Now, to simplify your expression, you need to factor everything to see if there's any common factors. We don't usually like to have a trinomial, which is what we have on top, with a negative in front. So I'm actually going to pull a -1 out first. That will change all of my signs, which is crucial to how this factors. On the bottom, we can pull out an r squared. That's what they have in common. On the top, you have a trinomial in here with a 1 in front of the r squared. So you just need factors of 12 that, since this is negative, they're going to be different signs that add or subtract. Since we're negative, we're going to be subtracting to the 1. This is a -1 here. So here's this rule, and we'll go over some more factoring in class as well. But if you have a negative in front of your c term, this is your last term of your trinomial, you are going to have multiplication of a positive and a negative number together. And then they have to add to the middle number, which if you're opposite signs, you're really subtracting to the middle number. So factors of -12 are 1 and 12, 2 and 6, 3 and 4. If we make it a +3 and a -4, that gives me my -1 for the middle. So this is -1 times r plus 3, r minus 4, all over r squared times r plus 3. Now it's a good thing that we tried to factor this because the r plus 3 is a common factor on top and bottom. So this is, you can pull the negative out to the front of the fraction. This is -r minus 4 over r squared. Now let's talk about that negative out to the front. Another way you could have done that is you could have left it as a parentheses on the top. That would have been okay. You could have distributed it across the entire top. We don't typically put negatives in the denominator, so usually you keep it either out front, and that doesn't change these signs because it's out front of the whole fraction, or you put it on top, and that can either stay out front of that or it can be distributed. So either one of those cases would be acceptable as well. Okay, let's look at B. Now B is a little trickier. This is to see if you actually first of all, we have to talk about what is division, and then we have to talk about how some of this factors. So when dividing two factors, we really multiply by the reciprocal. So the first thing we're going to do is we're going to flip this. So this is a cubed minus 8 over a squared minus 4 times, and you flip the second fraction, a cubed plus 8 over a. Now, the a squared minus 4, most students will remember that that's a plus 2 and a minus 2. Because that's a difference of two perfect squares. Where some people will fumble around and forget is the how do you factor if it's a perfect cube. So I did bring those formulas here. So here's the formulas for perfect squares. And again, we're going to do more factoring in class. So a squared minus b squared is a plus b and a minus b. A cubed plus b cubed is a binomial times a trinomial. The binomial is the cubed root of both of these. So cubed root of a cubed is a, cubed root of b cubed is b. The sign in the binomial is the exact sign that you had in the original problem. The trinomial is actually made up of making the a and the b multiply together in a pattern. This is the first root times itself. This is the first root times the second root. And this is the second root times itself. So really it's just multiplying whatever the cubed root of each of these is times itself, times each other, times itself. And then the rule for the signs is that whatever the original sign is, the first sign in the trinomial in between these two is always opposite, and the last sign in the trinomial is always positive. So we remember that by SOAP. So same as the original is the first sign, opposite to the original, that means this guy right here, and then always positive. So if you're subtracting two perfect cubes, then you get a minus first and then plus plus. By the way, you cannot factor this using real numbers. This is prime because there's no way you can multiply two things together where the middles will cancel and the sign at the end will be positive. So that is prime. This would factor using imaginary numbers only, which we're not quite ready for that, and it's going to be a while before we are. So this last example here, oh sorry, we need to go back and do the one with the division. Got ahead of myself. So let's factor these tops up here. So this is perfect cubes using our pattern. Cubed root of that would be a. Cubed root of 8 is 2. So this would be a minus 2 because it keeps that sign. A times a is a squared. A times 2 is 2a. 2 times 2 is 4. So I say I just did that pattern we talked about. And then SOAP, same as the original, opposite to the original, always positive. This guy factors exactly the same, except the signs are going to be a little different. It's a and then a plus 2, and then it would be a times a is a squared, a times 2 is 2a, 2 times 2 is 4. And then this one is same as the original, opposite to the original, always positive. So when we go ahead and get all of this here, we notice that there's an a minus 2 on both top and bottom, and this is times, so it can be either top with either bottom. And then we also get this a plus 2 cross cancels with this a plus 2. So our final answer is a squared plus 2a plus 4 times a squared minus 2a plus 4 all over a, because there's still this a over here on this denominator. Now that's, we're not going to make you FOIL out that top, and there's nothing else you can do with those because they don't factor. So that would be my final answer. All right, and then this is our last example for the pre-video. So when we're adding and subtracting with two fractions, we have to get a common denominator. So the first thing you want to do when you're trying to figure out your common denominator is factor all the bottoms. And this one's perfect squares again, so that's t plus 3 and t minus 3, square root of both of those, once with a plus, once with a minus. So I notice a theme here that I have a t plus 3 in both of these, a t minus 3 in both of these, and the most I ever see any t plus 3 or t minus 3 is one time per fraction. So my LCD is going to be I need a t plus 3 and a t minus 3 for all three of my denominators. Okay, so your next step here is that you want to set up what we call little fractions that are going to go beside each one, and you're going to multiply by what the denominator is missing so that your denominators all end up the same. And for this last one, I always just keep it as the t plus 3, t minus 3 in factored form. Now you don't need a little parentheses next to this one because remember that one already has the desired denominator of t plus 3, t minus 3. So this one is missing the t minus 3. Whatever you do to the bottom of a fraction, you have to do the same to the top to keep it balanced. And this denominator is missing the t plus 3. So whatever we do to the bottom, we have to do to the top. So now what we're doing is you're realizing that this whole denominator thing is over now your LCD. So this is my little trick. Not everybody does it this way. but I don't want students to cross cancel anything until we've completely simplified the top. So my next step after I set up all these is to write LCD at the bottom and just use that as a placeholder for this part until the very end. So now we're going to work out the top. We have a t times a t minus 3 plus a 4t times a t plus 3, and then the minus 18. So then we're going to distribute everything on top that we need to. So that's t squared minus 3t plus 4t squared plus 12t minus 18 all over my LCD. Add like terms, so I'm getting a 5t squared plus 9t minus 18. And now I've completely simplified what I could add with the top. So now I'm going to write my t plus 3, t minus 3. Now, word of a caution. You must always check to see if the numerator factors, because if it does, it could cancel with something in the bottom. It may not, but it could. So does the numerator factor? That's what we need to ask for this last part. So to check that, and again, like I said, we are going to cover factoring in class, so you'll get more of this practice with these skills. If you have a non-1 in front, you do what we call the AC method. You do 5, which is the front number, times the constant. So 5 times 18, and it's a negative 18, so it's going to be negative 90. We list the factors of negative 90. So 1 and 90. 2 goes into it 45 times. 3 goes into it 30 times. I don't believe, does 4 go into 90 evenly? It shouldn't, no. 90 divided by 5 is 18. We should have known that one. And 90 divided by 6, let's see if that goes evenly. 15. And 7 doesn't go, 8 doesn't go, I know those, and then 9 and 10. You know you've got your whole list when there's nothing in between these two, or if there is something, it just doesn't go into that number. So then we need a group that makes it it's negative 90, so one's positive and one's negative, but it needs to add to 9. So it looks like we need a negative 6 and a positive 15. So it looks like this is going to factor. So 5t squared, I'm going to put the 15t next to that. It doesn't matter which one as long as you get them both. And notice the 5t stays 5t squared, the 18 stays 18. It's just the middle term that gets changed. And then we do what's called factor by grouping, which is you look at the pairs and pull out what they have in common. We can pull out a 5t out of the first pair. That would leave me with a t plus 3. We can pull out a negative 6 out of the second pair. That also leaves me with a t plus 3. So this is t plus 3 and 5t minus 6. And boy, am I glad that I checked, because I would have missed points on a test if I did not realize that this is a reducible fraction. Because on top and bottom, I have both of them have a t plus 3. So this is 5t minus 6 over t minus 3 for our final answer. Okay, thanks for watching this video, and I will, you need to remember to bring, this is our first class session, so make sure you bring your notes that you filled in with this, and we will go over some more examples in class together. Have a great day.